For this video, you might want to pause along the way so you can do the steps that I'm going to talk about. I want to show you a nice quick way of using Newton's method. You should already know what it is, and this is really just to show you on the calculator. But quick run through. Let's suppose we're wanting this function here, this cubic. Here's the graph, and we're interested in finding where it crosses the x-axis. We can see visually there's 3 points. And let's consider, for example, if we thought a root, for example, was around 14. Maybe that was our initial guess. Okay. The idea of Newton's method was just that, hey, we're going to use a tangent line at 14 to approximate the root. And we see quickly that, well, no, 14 is not the tangent line, but we'll use the tangent line to find out where, in fact, does the root, or I should say, where does the tangent line cross the axis? And it should be with Newton's method that the tangent line is closer of an approximation. And if that first place isn't close enough to the real root, what we do is we'll find the value here at this new point and find a new tangent line to that point and find where that new tangent line crosses the axis. And it's a repetitive process going on and on. So saying we're going to guess 14, we want to write the tangent line to the guess. And actually, Newton's formula that we'll come up with does this shortcut. But I do want to remind you, it is all about tangent lines. There's our standard idea of writing the equation of a tangent line here. We're interested in solving this for x because we want to know where x crosses, and then we get this formula in general. And here's the process overall for Newton's method. We make some sort of an initial guess at where the root might be. We use that formula, which was just this thing right at the bottom here, where we solve this for the x value, okay? And then we just repeat that step over and over again to the desired precision, okay? The idea is you pick a guess. What this gives you is that guess, or I should say, where this is where the tangent line actually crosses, okay? So that's where the tangent line crosses the x-axis. But then what we do is we take that value, as I said, and we put it back in, and we get a new point, and so we plug the new x value in, get the new point where the new tangent line crosses the x-axis over and over. So taking this particular example here, what we want to do on the calculator is we're going to plug in both the function and its derivative into the calculator, okay? So on the calculator, this is where you might want to pause, type in the function that we have here, the cubic, into y1, and into y2, plug in the derivative. So get that entered. Now that you have that entered in your calculator, we are going to go just into the home menu here, or the home screen, and we're going to type in our initial guess. I said we were going to guess a 14 on the picture, and with the 14, entering the 14, we have to hit enter, so sort of like we've primed our initial guess. This is now what we consider the x0 to be 14. Then we're going to type in, essentially using this formula, but this formula we're going to say, oh, the 14 we've typed in is the current x guess. So we're going to use the answer feature on the calculator, and on the calculator then we're going to type answer minus y1 of answer over y2 of answer, because y1 is the function and y2 is the derivative. So type that in. So when you type those in like this, you get the y1s out of this VARS, the variables button, okay? So it should look like that. Now when you press enter, that's where your tangent line crosses the x-axis, and it should be near the root. But if it's not near enough, which usually the first guess isn't, all we have to do, the nice thing about having it primed with the answer, is you press enter again, and it has plugged this current value in back into the function. This is now your second guess. And you do this a couple of times until you get the desired degree of precision. You see that I've only had to press it a few times to see that degree of precision. So this down here, x6, we've got it precise to as much as our calculator can show. One more example. So just remind you here, we found uh, at least approximately to however many digits this is, like 10 or so, the root that we see on the graph here. But there are other roots to the same function. So, keeping the cubic in y1 and its derivative in y2, we can once again just type in an estimated guess to start with. So for example, we've got a root that looks like it's near the origin. So if we just type in, on the calculator 0 to prime the derivative, or I'm sorry, to prime the x value, then we can use second entry twice to get back to my formula here, right? What we're going to do again is this is going to be 0 minus f of 0 over f prime of 0. That's what's going in. You press enter, and it's giving you an estimate of the root. I press it again, it'll be this new value, the 0.136 minus f of 0.136 over f prime of 0.136. And all I have to do is hit that a bunch of times. Boom. There's my answer, right? So, we typed in, just quick review here, my x0, my initial guess was 0. I typed that formula in, so this was our first iteration is x1, x2, x3, and you see after x3, I don't see any differences. So it's precise. It's precisely getting us the answers to as many digits as we can see with very little effort. Okay, you just have to remember the formula. We see that it looks like there's another root over here. Looks like around -12, so I'll type in -12, enter, and then go get second entry twice to get back to my formula, and enter a bunch of times. Oh, I guess it's not quite -12, it's -0.9356536, close enough. Okay, let's look at one other function. Everybody knows pi, and here we're going to use Newton's method to approximate pi using the sine function. So we know that the sine function intersects, of course, at 0, at pi, at 2 pi, etc. But suppose we didn't know the decimal approximation for pi. Well, we can use Newton's method to estimate this, and we'll say, well, look, we think pi is close to 3, so we'll use that as our initial guess. That would be reasonable. So remember, in our formula, any particular value, we just need to say, look, it comes from the previous guess minus f of the previous guess over f prime of the previous guess. That came, remember, from the tangent lines. And we know the derivative of sine is cosine, so literally all we're going to do on our calculator is plug this stuff in. Let's see here. Let me get the calculator back. If I can. Calculator won't come back. Help, calculator. Get the calculator again. So you might want to pause the video. On your calculator, y1 should be sine, y2 is cosine. Okay. And then what we need to do is prime this up. I think that pi is close to 3, so I set that 3, enter. And then I need to set up my formula. Remember this formula, so it's going to be the answer minus the function at the answer, so I get that as y1 of the answer, and divided by the derivative, which is y2 of the answer. And it's all set. So I'm guessing pi is about 3. I press enter. Okay, that's a better approximation for pi. That's a better one. That's slightly better. And now I can't tell the difference between that and any of the other guesses. So, here's our x0. And after that x0, we got this to be our x1, x2, x3, x4. And we get really good approximations for pi. Not in radian mode, just a warning here. If you try to approximate pi in degree mode, so I say I think pi is about 3, and I switch this to degree mode now. So when I use the formula and start pressing enter, ooh, not good. That doesn't look like pi at all. So watch out, those of you in degree mode. You don't know pi.